Ready? Okay, so let's get started here. Before starting with moving to SuperLU, I'd like to call your attention to the survey form that you can, so if you go to the workshop website, would like you please to fill this form and send your feedback to us. It's anonymous, so you can be very sincere in your remarks. So, all right, so oh gosh. Okay. I'm not Sherry Lee. Sherry's somewhere around the Gobi Desert in China, attending a meeting there. And she asked me to present her slides. I think I'll be able to answer most of the questions, let's say, because I kind of know what is going on behind the scenes in SuperLU. So SuperLU is then a library intended for solution of linear systems, sparse linear systems. It can also be used as preconditioner. You can generate preconditioners with it if you have, for example, a Krylov kind of solver. It has been funded over the years by DOE and under different projects. Sherry has collaborated with a number of people here in the United States, in France, and others. So the library can be downloaded as all libraries here that people have been talking about. The speakers have been talking about. In this workshop, the libraries are free. And one of the important things is that you are, again, like other libraries, you are supposed to link to a fast library that implements the BLAS, right, for performance purposes. So then in this tutorial, I'm going to talk about the functionality, a little bit of the SuperLU, background of the algorithms, the data format that's required, and some examples as well. And in this afternoon, we're going to have some hands-on, and we'll have an opportunity to compile a few examples and see how to use SuperLU. This may be already very well known, right? For I guess you may know this already, but that's basically what it is. You have a sparse matrix here. And the definition of what a sparse matrix is perhaps sometimes not so well defined, but it's basically if you have a small number of non-zeros, depending on what you do in your matrix, entries that were originally non-zero, or rather entries that were originally zero can become non-zero. And during the factorization process that we're going to take a look at. And this is something that you have to consider if you want to keep memory or storage under control and also to have performance. And this is what we're talking about here. For example, for a matrix of a dimension 1,000,000, 10 to the 6, it's often the case that you have only 10 to 100 entries, non-zero entries per row. So in that case, then you have a sparse matrix. So you have to be then, to pay attention to keep it, to benefit from the sparse structure. And the matrices like this show up in a number of different applications, from fluid dynamics to statistics and electromagnetic and data analysis, engineering, and others. And here are two examples. The one to the left is a matrix, and you can find this matrix in the Matrix Market collection. It's the one coming from Boeing. And the other one, I don't know what it is. I don't know the application it comes from. This is probably some sort of finite element or structural model. Now, so if you have to solve a system of linear equations, well, if you still remember my presentation on Tuesday, Scale-Pack was intended for dense. Right? So now we shift gears here. We talk about sparse. So then if you are solving a linear system, Ax equals B, where A is sparse, that's worth many zeros in A, that's worth a special treatment. Depending on the size of your problem, on the properties also, you could try to solve, or you could solve the system using an iterative method. And what happens is in an iterative method is that A is not, you don't change A. Basically, you do matrix vector kind of operations in order to generate an appropriate space, usually Krylov. But if your application is, sometimes applications are very complex and iterative methods may not converge in some cases, then you may have to resort to direct methods, where you do modify A in the sense that you factor A as the product of 2 or 3 matrices, as we'll see. And one of the big differences is that in contrast to iterative methods, direct methods are harder to optimize and parallelize. Iterative methods are much easier to do that. Direct methods robust, right? But they imply higher algorithmic complexity. So this is basically then a trade-off that you have between iterative and direct methods. And it's often the case that you can use a direct method as a preconditioner for iterative methods. SuperLU is not the only high-performance solver out there. So Sherry has done a survey, actually, of a number of solvers. There are, for example, solvers for sparse symmetric positive definite matrices. Then we are talking about LLT kind of decomposition. The composition for symmetric indefinite matrix. L is a lower triangular matrix. If you have a symmetric indefinite matrix, you can do an LDLT, where D is a diagonal, 1 by 1 or 2 by 2 blocks. If you have a non-symmetric matrix, you can do an LU decomposition, where U is upper triangular. You can do a QR in some cases, and so forth. Okay. These days, you can have implementations. You can have sequential shared memory using, for example, OpenMP, or distributed memory using MPI for those methods. And there are also some libraries that provide out-of-core implementations of those. As I mentioned, SuperLU is not the only one out there. So there, in the back of the room, we have some of our colleagues that have worked on MUMPs in France. There is also PASTIX from France. This one was developed by IBM, WSMP, and others, right? And you can access particular SuperLU, the distributed one that we'll focus on, from PETC, Trilinos, and so forth. Then LU is a kind of general library in the sense that it's intended for non-symmetric in principle, but you can also deal with the symmetric matrices and get good performance. It performs an LU decomposition and then followed by a triangular solution. Often in this, when you are dealing with sparse matrices, you have to do some ordering. There are many different ways of doing ordering. And that's to preserve the sparsity of your matrix, right? And by preserving the sparsity, as I mentioned before, you can keep memory usage under control, and you can also have, gain in performance by keeping control, paying attention to the sparsity. In some cases, you have to do an equilibration like this. You take your matrix A, the input matrix, right? And you have to do some sort of balancing or some sort of permutation of rows and columns in order to have better numerical properties, and also, to better deal with the sparsity. And SuperLU also, in particular for the distributed case, where changing rows and columns in order to keep stability, numerical stability, that may have a big impact in performance. There are ways that you can, techniques that you can implement to, after you compute a solution, you can do some sort of refinement of the solution, to make And that's what I'm talking about here, iterative refinement, in order to, as the name implies, have a solution that's closer to the problem that you are solving, right? What is the status? There are basically 3 implementations of SuperLU. It doesn't mean that they are, for example, the distributed version is just the parallel porting of the sequential one. There are differences in the algorithms. But those are the 3 versions. There is the sequential version, right, the serial, basically written in C, the 3 versions. Then there is the multi-threaded version. Sorry, I heard something. Is there a question or a comment? So then that one uses P threads or OpenMP, right? And there is the distributed version that's implemented on top of MPI, as all other libraries you have heard about during this workshop. The precisions, it comes in real, complex, single, and double, right? And it provides also for interfaces for Fortran. So the multi-threaded version is similar to the serial version, both numerical and in usage. The difference here is perhaps the SuperLU dist because of the way the data is distributed. And that's an interesting, you might want to ask, why single precision? Our experience, and even working with other packages, is that when you are doing development mainly, some numerical problems can be detected in single precision, and they are going to show up much later in double precision. So for the kind of development that we have done here in Berkeley or in Tennessee, the teams working in LAPACK, ScalaPack, and other libraries, we always do development in single and double. Because, as I mentioned, sometimes errors show up in single precision, and they are likely to take longer to be discovered in double precision. Well, that's just a sideline here of mine. Okay, so SuperLU has been adopted by a number of libraries in industrial applications, like the Cray library. If you buy a Cray computer, SuperLU comes with this LibSci, and HP, and also others. And it has been used in a number of applications of interest to the US Department of Energy, for example, in plasma physics, and also in the design of linear accelerators. Just here, a quick review of Gaussian elimination, which is basically the building block for this kind of direct solvers. That's a small matrix A there that we are basically, writing it by blocks, where here we have only one entry, and here we have a row and a column, and that's the remaining piece of the matrix. Basically, what you do, you can write this matrix as the product of these 2 matrices, and then you can get this relation for C, right? This is the remaining block. And that's basically what you try to do when you have a big matrix. By doing this, you can move further, and you can compute factors like this, and then you have the decomposition of A into the product of 2 matrices, just by looking at how it works here and doing this kind of update. Okay, so that's the basic thing here behind Gaussian elimination. And once you compute these factors, and then, so what's important is then once you get C, you would apply the same kind of decomposition in C and continue, right? And once you compute the factors L and U, you would proceed by dealing with the 2 triangular matrices and get the solution X given a right-hand side B. Okay, so it's very simple. I mean, pictorially this is very simple, but then if we have all these things here in a sparse format, then of course the implementation becomes trickier. And now we get back to what I mentioned before. We have to pay attention to fill-in, which is basically positions that were initially 0 because of those because of the decomposition, we are trying to write an original matrix, say, as a product of two matrices. Entries that were originally 0 may become non-zero during this decomposition process. And this is what this picture here shows. The black dots were the original non-zeros in the matrix. Okay. So that decomposition in the previous slide can be basically written as, it's a nested at a 3-level loops, right? And basically what we're trying to do is given an entry jk, it's updated like that. Again, I refer to the previous slide to see how that works. And then originally we have the black dots here. Those are the non-zeros. But when I apply this loop here, these 3 loops, I get some entries that were 0, but it become non-zero, and those are the reds. Okay, so then this is what the fill-in is about. So then we have to rearrange the loops. There are many ways of rearranging those loops, actually, and then we have many. We refer to left-looking way of decomposing the matrix, or right-looking, and so forth. But what we try to do in direct solvers is to do some reordering in order to have as many, or as little rather, red entries as possible during the factorization process. Okay. And this is for, just to give you an idea of what happens here for 2-dimensional problems. The number of non-zeros that are going to be added, right, because during the factorization are of the order of 10 times than the original number of non-zeros. Okay, so to take the number of non-zeros that original in the matrix, multiply by 10, this gives you an idea of how many entries, non-zero entries, you're going to have at the end. This is for 2-dimensional problems. For 3-dimensional problems, it's higher. It's in the order of 30 to 50 times the number of original entries. So this is the memory then that you'll have to think about, right, that we're going to need for the factors L and U. It could be more than that, and much more, actually. Compressed row storage is the one that's used for storing the matrices that SuperLU needs. Basically, given a matrix like this, the entries on the diagonal here are given by numbers, the others by letters, just to simplify the representation. And in order to store that matrix, you need 3 vectors. You need a vector which basically stores the position, or rather, first, the non-zero entries of the matrix. For example, for the first row, I have 1A, the second row 2B, the third row CD 3, fourth row E 4F, and so forth, right? I also need, this is then a floating point array that you need to store the data, the entries. You need an integer array to store the pointers, the column indices for each one of those rows, for example. We know that for row 1, there is an entry in row in column 1 and another entry in column 4. For row 2, there is an entry in column 2, another entry in column 5, and so forth, right? And we need a third array, an integer, which tells us where each one of those rows and the corresponding indices start in these 2 arrays that we have here. For example, the first row starts in position 1, the second row in position 3 in the array, the third row in position 5, and so forth. So with this kind of data structure, again, CRS for compressed row storage, we can store a sparse matrix. Here I'm doing by row. We could do that by column as well. We could, instead of storing by row, we could store by column. And there are other storage strategies that we could use for a sparse matrix. And then for this example of dimension 7, right? It's a 7 by 7 matrix. With 19 non-zeros, I need NNZ reals, number of non-zeros. And then that's basically the sum of two vectors here, the number of entries, NNZ plus N plus 1 integers. And then with this, we can basically store a sparse matrix. And as I mentioned, there are other data structures that we could use. So here, the idea for a sparse solver is to use blocks during the factorization. And that goes back to what I mentioned on Tuesday. That's basically, to allow a better use of cache, usage of cache, and also blast 3 level of matrix kind of operations. Then, so if perform an LU decomposition, I'm gonna work with a block, a diagonal block, that's going to be used to update entries that are down in the matrix. And we refer to this as a supernode. This is a supernode. There are updates, calculations being done here in the supernode. For example, row 6, 7, 8, 9. I can have a graph like this. So the supernode involving then columns and rows 6 to 9. And once I compute this, the factorization for this block, I can update rows 15 and 25. And that's what is happening here. Okay. And with the dashed line, as you can see, the impact here of the various rows into the rows in the supernode, in the block, in the rows below it. So in sparse factorizations, usually, as I mentioned before, you do permutations. This is usually happens, it's in a transparent way. The user doesn't see these permutations happening. But basically, you take your matrix and you apply a permutation to the right and the permutation to the left, and then you compute the LU decomposition. Again, that's for numerical stability, also to maximize parallelism and to keep the fill-in under control. Basically, then what you do, in a direct solver, there are different phases. You perform first the permutations to order the equations and variables to minimize the fill-in. Then you do a symbolic factorization to identify the supernodes and to prepare to set up data structures, allocate memory, and then to prepare for the numerical factorization. This is where the number crunching is going to happen. And this dominates total time. And then next you do the triangular solutions. This is usually doesn't take much time. If we think in terms of performance, it's often the case that here this part of the calculations is scaled better than this part here, the triangular solutions. Do you agree with that? So then there was a question in one of my slides on Tuesday. I showed the performance of the decomposition plus the solution. And one of you, I don't remember, who asked me, well, these two things are separate. How would that look like, right? So basically, again, so this part here scales better than this part here in decompositions like this, or in direct methods rather. So numerical pivoting. This is what is the goal here? Is to prevent element growth during the calculation, during the computation of L and U. What do I mean here by element growth? We don't want to have a division in which the denominator is a very small number. Okay. Otherwise, if you take something and divide it by a small number, what happens? The result would be very big, and this may have some implications later on during the factorization. We don't want that to happen. And in order to kind of try to control this or to prevent that from happening, what we can do is to swap rows. We can swap rows, right? For example, if this is a small number and this is bigger, we swap these rows, and instead of doing the factorization here, we proceed with this. We could do that, but we could do that by columns as well. Okay. In a sequential mode, that's if you have a sequential implementation of an LU decomposition, that's relatively easy to do. If you're going to do that in parallel, that's a nightmare. If you're going to take a matrix that's distributed among, you name it, a certain number of cores or processes, if you're going to swap rows and columns, you're going to pay a big price in terms of performance. Okay? So that's one of the reasons that the sequential version of SuperLU and the multi-threaded version of SuperLU they actually do the spatial pivoting, right? But not the SuperLU, the distributed version of SuperLU. So this uses the distributed version of SuperLU uses a static pivoting strategy, which before the factor, it tries to do these permutations to see if we can look ahead and do some to see if we can can control a sparse and also the numerics that are going to happen before. There are ways that you can replace tiny pivots by taking into account the norm of the matrix. But then, if necessary, as I mentioned before, at the end of the composition, the solution of the system, it's possible to do some steps of iterative refinement, which turns out to be quite stable. So this is then basically a trade-off here. We don't do the full pivoting or the partial pivoting as we do there, and that's for performance reasons. The ordering. So again, the ordering in the matrix is important to minimize the fill-in, and there are a number of different ways of doing it. For example, there is the minimum degree, there is Cauchy-Hillman-Key, and others. Depending on how your data, depending on the implementation of your algorithm, there is things like that would work better or not, right? For example, SuperLU here applies minimum degree to reorder the entries of the matrix, and in order to also to get those supernodes that I mentioned, showed to you in some of the previous slides here. And also, by applying this reordering, you can have you can redefine the order in what the elimination or the LU factorization is going to happen. Another way of doing this, and this is for example, the nested dissection strategy. And this works well for 2D grids where basically, for example, if you have a big grid here, right, you have the points, basically you can have this lines splitting the grid, the reds and the blacks, and you could do the same, apply the same strategy among each one of the sub-blocks. And this helps when you are going to do the LU factor. Okay. There are the nested dissection ordering. Basically, if you have a matrix, it tries to identify the boundaries. For example, for this matrix here, identify the blocks, and it identifies the boundaries. So basically, you could do this factorization independent, A and B, and then update where the entries, where the X's and the S are. Okay, so then that's the idea of these orderings. And the goal here for this nested dissection ordering is to find the smallest separators in order to have big blocks A and B here and have just a little here to be updated afterwards. And this is how this is what it looks like here if you apply the next dissection. Let's see what we have here. So this is a 2D mesh, two-dimensional mesh, right? So if you don't, this is what the matrix A looks like. It's a sort of a block tridiagonal kind of matrix. So if you apply the nested dissection ordering, this is what they make. Then there's a permutation on A. This is what the matrix looks like, okay? And if you then, after the LU decomposition, this is what the LU factors would look like. And here you can see the blocks, right? This is one, this is another, and these are the separators actually. This is one block here, one block, one separator, one block, another separator, and so forth. But again, with this strategy, the idea is to keep, this is ordering strategies, the idea is to keep the fill-in under control. And it allows for parallelism as well. There are a number of ordering strategies that you can use in SuperLU. For example, you can use an ordering based on A transpose A. You are actually not going to compute that product. Okay, you never do that. A transpose A, never do that. But there is a way that you can do some sort of ordering just by figuring out what the structure of A transpose A would be. Another one that can be used is A transpose plus A. You can compute an order for that. So there are all a number of orderings, as I said, that you can use for pivoting purposes. And similarly, there's a number of techniques there that, for example, diagonal Markowitz, hypergraph, and others that I just have some idea about, rough idea about. One thing is that SuperLU comes with a built-in ordering strategy, but if you would like to use another ordering that you think would work better for your problem, you can feed that into SuperLU as well, and SuperLU will take it, the ordering that you prefer. For example, you can, there are some C constructs there that you can basically set default options, and for example, for those of you who are familiar, you can use matrices to compute the ordering, and then you would give that to SuperLU. Or you could use pastics. It's not pastics. What is the ordering there from Bordeaux? Scotch. So yes, there in Bordeaux in France, there is another library that does reordering. It's called Scotch. You could use Scotch to compute a permutation, give that pass that to SuperLU as well. So the symbolic factorization. Remember, so here there are a number of steps when we talk about LU decomposition. First, we do a symbolic factorization before doing the actual computations, the number crunching, just to figure out how much memory the solver is going to need to prepare for that, and also for pivoting. Okay, and so then when you do that, you can figure out what is needed. You can identify the supernodes and so forth. So the symbolic factorization is important before getting to the numerical factorization, right? So in the sequential SuperLU, so basically the idea is to reuse data as much as possible. And what we can do here is by having this idea of keeping things in a block, or in this case the supernodes, we can use level 3 BLAS, the matrix kind of operations, right? The multi-threaded version of SuperLU exploit different levels of parallelism at both the coarse and the fine grain levels, and also it uses scheduling to minimize the runtime. Now, in the SuperLU dist, the one that's implemented on top of MPI, there is no partial pivoting happening there. So basically, you are not changing the order of the rows and columns, because as I mentioned before, this would be very painful to do in parallel. And here, it uses the concept of a two-dimensional matrix distribution, which is similar to the block cyclic distribution that I talked about on Tuesday, the one for scale pack. But this is transparent to the user. What SuperLU dist takes as input is a matrix in compressed sparse row. Okay, and you'll see this in the coming slides. The redistribution of the data in the block cyclic is done internally by SuperLU. The user don't see it. Okay. Let's see here. So the SuperLU version, the one that's uses OpenMP. Actually, there are two implementations. You can use either pthreads or OpenMP for the multi-threaded version. For those of you who are familiar with this kind of how the algorithm is structured, it implements a left-looking strategy. Compared to the sequential version, this is the kind of speed up that you can get. Actually, these are all the numbers here. You can see 1999, but it's over speed ups of over 12 times if you are using a machine with 16 CPUs in a shared memory environment. I would say that these numbers the speed ups maybe even look much better these days. Okay, so this is the way it works. Basically, these two factors here, you have during the calculations, you get these pieces of U and L, and you proceed like this way with the calculations, updating the panels of the matrix. And you can do that in parallel by means of this thread implementation. Now, the distributed version, it's based on top of MPI, as I mentioned before. It uses the two block cyclic layout, and you can perhaps recognize here the block cyclic, right? If you think a little back into Tuesday. So this would be the process 0, 1, 2, 0, 1, 2, the same for the rows. And then you proceed from here, and this is how things would be updated as you go down the matrix. And with this strategy, it has been shown that you can get very good scale on thousands of processes or processors, right? Let's see here some performance numbers for SuperLU. This was on an Intel and also on a Sun, Victoria, the Clovertown first, and then the Victoria Falls. And this is the kind of the dimensions of the matrices and the applications the matrices come from. The first one from an economic model, the last one from some sort of a circuit design. Dimensions of the matrix from 59,000 up to 120,000. And the number of non-zeros here in the matrices. And you can see the fill-in, right? The fill-in in the multi-threaded, the fill-in and the distributed version. And you can see this is the average of the supernode, how many rows and columns you have per supernode. But you can see here what's important is this, as I mentioned, this is the number of original non-zeros. You can see how many more non-zeros are introduced during the factorization. For example, this one here had this is a 3D finite element difference approach. It's modeling, I guess, a stomach of something. So from 3 million during the factorization process, the number of non-zeros multiplied by 4, more than 4, right? Actually, no, 40, right? So from 3 million non-zeros, this is what you get in the factors, 136 million. Right. This again, I had pointed out to this. For 3D problems, the fill-in is much more important. What about the performance? Let's take a look here. For example, if you increase the number of threads, what's the megaflop rate that you get? For 4 different matrices, some of the matrix, for example, the famous one, the stomach from the previous slide, you can see, how the performance of the solver goes up by increasing the number of threads there. Now, so that's for the SuperLU multi-threaded version. If you compare, with MPI, for example, if you do the number of threads or tasks, you can see that the performance here, there's more variation. If you are using, what is this number, speed up that you have, if you compare the p-threaded version over the performance of the MPI version. Okay, so there's some variation there if you are going to compare the performance of the two implementations, also because there are differences in the algorithms, in particular in terms of the pivoting. So that was for the Intel. These are numbers for the Sun Victoria Falls. Again, in this kind of platform, you can have more threads. This is the megaflops rate, and you can see that gets to a point that you don't, and we saw that with the dense linear algebra, right? For scale pack, after after a certain number, if you keep just increasing the level of parallelism, it doesn't mean that the performance is going to get any better. So that's what you see there, okay? And that's what we have in that slide. So what is the user interface here? First, what the user has to do is to distribute the input matrices using the compressed sparse row format. For example, for this matrix A, you could, so if you are going to use 3 cores or 3 processes, you would have to distribute the matrix by blocks of rows. Similarly, for the right-hand side, right? Here's the solution is going to be overwritten on the right-hand side. This is perhaps this is certainly easier than the block 2, the 2D block distribution. It's natural for users to do this kind of distribution by rows. And this is what is done by other packages, as PETC, for example. And what then you have to do is that for each one of these blocks of rows, you have to use that compressed sparse row format and give that to SuperLU. Let's see, I think I have a slide about that later. And so each process involved in the factorization has information related to the data, right? That's local, and this is done in a structure like this, where you have information about the number of non-zeros in the local submatrix, the number of rows on that particular process or process, the index of the first row, and then those 3 arrays, right? The pointer to first one array that are basically pointers to the non-zero values. Another one is the column indices, and that's the beginning of the row in each one of these previous 2. This is basically then the compressed sparse row format that's done for each one of those blocks of rows. And for example, for an A, a matrix A that's distributed in 2 processors, or like that, okay, P0 and P1, this would be then the data structure on P0. You can see that for that block there at the top has, it's very weak now. My battery is gone. So you can see that that block at the top has 5 entries, while this one here has 6. The one at the bottom, actually, it's 7, right? 3, 4, 7, yes. And then for process 0, number of no zeros 5, 2 rows, a first row starting in 0, okay, and this would be the entries, else, U, LU, and so forth. The indices and the pointers for the rows. And the same thing for P1, now 7 non-zeros, 3 rows, where it is starting. The first row in that process is LP and so forth, and the indices and the pointers. So then you do this. In one of the first slides in this presentation, we had that for a big matrix, for a full matrix. Here you do that. You apply the same representation for each one of the blocks or the local submatrices. The idea then is to we apply. So we can we have here the if we are so if we think about the process grid and the MPI communicator here, we can use this to solve a preconditional linear system. For example, if I have a matrix, a system AX equals B, I can multiply by the diagonal of a diagonal matrix, actually a block diagonal, that's formed by those blocks A1, A11, A22, and A33 for this small example. And then we can use a SuperLU dist for each one of these diagonal blocks, right? I could apply, instead of applying SuperLU to the whole thing, I apply just to each one of the blocks, and then I could use that as a preconditioner, depending on the application that you have. And with that, in order to do that, I can basically create different process grids, right? That would be the MPI communicator. So to keep things separate, I would define a communicator for this, and for this, and do all the calculations independently from each other. And again, apply that for, use that as a preconditioner, say for, I don't know, multi-grid applications, that kind of stuff. And then that's what you would have inside each one of those blocks, right? Again, we would have this notion of the block cyclic 2D applied to each one of those sub-matrices, but that happens behind the scenes. The user doesn't see it. There are basically two ways to create a process grid. So you can call the SuperLU grid init or function, which then maps the first rows of your matrix, NP row by NP call, into the communicator, the MPI communicator that you have defined. Or you can use a grid map that does a kind of more arbitrary distribution of your data. And this looks somehow, it's similar to what we saw with the blocks. You know, the blocks concept for the scale pack, right? That layer that sits, say, on top of MPI, but does everything that's needed for linear algebra to make things, to simplify things. It's the same thing. What the blocks do there for the blast, for scale pack, here we have grid init and grid map for SuperLU doing that kind of grid creation. And then you would define your data, the distribution of your data based on, of course, on the grid that you specified. Now, performance of this SuperLU dist on larger matrices. Matrices with dimension going from 800 to 1,000. Actually, it's not in order. Matrix of a dimension of 800,000, but that's real. A matrix of smaller dimension to 59,000, but complex. And you can see here here basically what you're doing is, I think this is the most important part of this column is the important one here. You can see the fill-in in the matrices. Given the number of non-zeros, you can see that in some cases the fill-in can be very, very big here, 600 times. Okay, for some sort of calculations for DNA, involving DNA. But so again, here you have all matrices in real and in complex that you can do with SuperLU. And for these examples, for these matrices, Mattis was used to compute to do the reordering for A transpose A or A transpose A. But of course, you don't compute that explicitly. You can do that symbolically. So these are results, some results on the Cray XE6. That's the Hopper Cray that we have at NERSC. Unfortunately, you have not been using Hopper for the hands-on. You have been using Carver, right? So at some point, this machine was at the number 5 on the top 500. I don't know where Hopper sits now. It's not 19. Things change fast, very rapidly. So that's a machine with the AMD Manicourt AMD processor, right? Chip, 24 cores per node. And here, so for the matrices that we saw in the previous graph, you can see what is the time it takes for the factorization, right? increasing the number of cores going from 8 to 2048. This is a log scale here. And you can see that as you increase the number of cores, not for all matrices, because then you would be dealing with the small matrices in each one of the nodes, right? That would the same kind of picture situation that we saw with the scale pack. It's not always the case that just by increasing the number of cores or nodes you're going to get smaller. Computing time is going to be reduced. But this one here, the cage 13, I think this is the NA application. You can see that the time basically went down all the time up to 2048 cores. Here there was some sort of fluctuation for that matrix that I don't remember what it was. I think it's in circuit simulation.
Correction. It's number 16.
Oh, it's number 16, not the number 19. Thank you, Tony. Oh, the Hopper is number 16 in the list. So this is the circuit simulator. There was a big drop here in the time. That's good, right? But then it went up, perhaps because of the way the ordering was done, or the data distribution, or this could be further investigated. But it's not the purpose here. It's just to show you how things, the kind of timing that you, by increasing the number of cores, you could see things happening, things like this happening. Now, so this was for the factorization, and then we can do the same kind of graph here, a similar graph using the same number of cores, and for the triangular solution, right? And you can see that for the matrix, the DNA one, the picture is it's kind of a similar kind of curve, right? Basically, for all of them, the shape of the curve is about the same that we have in that graph. But of course, let's see what happens here. Let's tend to of course, the units are different, right? Because the triangular solver takes much less than the factorization. Now, so since 3 years ago, so there is an interface in SuperLU for going back to or with SuperLU 4.0, where you can compute an incomplete LU factorization. What the incomplete LU factorization means that during the factorization you drop certain entries, in particular if they become very small. Why to do this? Well, because then, again, it's storage and also performance. But this is basically for this kind of incomplete factorization is intended for preconditioning iterative methods. Okay, so if you have an iterative method, that's one mechanism that you can compute a preconditioner, incomplete LU, and you can do that with SuperLU now. Okay, so in the examples that come with the library distribution, there is one there where there is an incomplete LU factorization that's used as a preconditioner for the GMRS. Okay. So now for this incomplete decomposition, there are some new rules there when to drop elements, right? And how this can be exploited during the factorization process, the incomplete factorization process, and also to improve performance, right? Because if you are computing a preconditioner, you want your preconditioner to be good, but also you don't want to spend much time, ideally, computing that preconditioner, okay? And for the test matrices that have been used for this ILU preconditioner, 232 matrices, the incomplete LU with GMRS converges for 60% of the cases here, right? And it doesn't converge always, but which means that depending on the application, you may have a better preconditioner than an incomplete SuperLU. But that's, the success rate, 60%, which is, I think, pretty good. This incomplete LU factorization has been applied to code in magnetohydrodynamics. This is for applications in fusion. And this was an array that we had previously to Hopper, an older model there at NERSC. And you can see here for the dimensions, of this matrix from fusion from 17,000 to more than 500,000. This non-zero number of non-zeros in the matrix ranging from 2.7 million to 95 million. And here the times that, here also we have the time for the computation of the factor, the fill-in, and the times. I don't know why she didn't put the times here, but we can check if necessary. And here you can see how many, the time that GMRS took and the number of steps it took to converge using the incomplete factors as preconditioner. Basically, by dropping entries, you can keep the fill-in ratio just 9 times more than the original number of non-zeros, just by dropping entries when they become small. And of course, this, one of the gains that you have is in terms of the time you take to compute the incomplete factors. That can be 10 times faster than instead of computing the full factors.
So what's the number of nodes in this computation?
The number of
nodes, like used for the
nodes?
Yeah. How many percent?
Oh, let's see. It's perhaps, yes, yes, yeah. The incomplete LU is available only for the serial. Yes.
Even for the latest release?
It's available only SuperLU 4.0. It's not the sequential version. It's not available yet for the distributed version. Okay?
I'm not sure. The shaman, the threads may have this.
It could.
Because she has a new version, but I don't know if she released it. That may be in there.
I don't think it has been released, but
No.
yeah. So if you suspect you are not getting the performance, right, that you should be getting, so the first thing to do is to check the ordering, right, for the sparsity. Also, diagonal pivoting. The pivoting is important. So, for example, if the matrix is diagonally dominant, there isn't much to be done there in terms of pivoting. Also, you need a good BLAS library. If you just download the BLAS from Netlib, and that's the reference BLAS, as we usually call them. If you just compile those and link to SuperLU, the performance may not be as good as, for example, if you're going to use the MKL, which is the Intel library, or AMC, what is the AMD one? AMCL, right? ACML. Well, I always get the things transposed here. The ACML, the AMD one, or others, right? So, and of course, you may have to adjust, since some of these tools, for example, Atlas, you can use to generate, optimized BLAS. Basically, we're talking about just the block size here for the target architecture, right? So you can get better performance. And what concerns the BLAS, if you can do some sort of automatic tuning for the block size, that's still an open problem. There's still some research going on there. I think with this, this is here in the set of slides where we start talking about the exercises, and I think we can focus on those this afternoon. And if you have questions.
So let's thank Osni first.
I had a question. Suppose I'm going to factor once and then solve 100,000 times.
Yeah.
Are there any tricks? So I'm just doing the back substitution, right? Lots and lots of times. Are there any tricks to actually make that go faster? Have people thought about how to improve the parallelization of the back solve? I'm thinking, for example, you may not want to do it, but you could factor twice, right? And have two different factors, so you could sort of back solve on half and the other half in parallel. If you know what I'm saying, right? You could.
No, I understand what you're saying, but I have never seen anything like that.
Okay.
So another thing, perhaps, that you were saying, if I'm going to solve 100 times,
100,000.
100,000, say, perhaps there is even, I'm just, perhaps what could be done is to see what the performance is and see if we could do some sort of what people have been talking about these days is even binary rewriting, that you can do this during the fly, right? There's some folks there in Maryland doing this, and also Mary Hall in you basically take your code and you modify your code, the binary, during the execution. And they say that the price for doing this is not high. So then what I'm trying to say here is, for example, if you look at the performance of your triangular solves and to do some sort of analysis, is it possible to change things without recompiling the full thing in order to get better performance? In particular, because you were telling me, what about solving the system 1,000 times?
Right, but I guess in his case, he's talking about load balancing, stuff. So as you start, you compute those factors, then you could start, some processes can start solving some of the systems. I mean, you have one right-hand side at the time where you can imagine that you can start distributed, so several will be computing the right-hand side. So, I mean, it's a great idea. I don't think it's implemented inside there yet.
So I'm saying, so if you factor your matrix once, the problem with the back solve is, right, you have to you start solving for, your last entry and you work your way back, right? But if you had reordered the matrix, and you could, when you started solving, you could be actually starting to solve different elements in the matrix, right?
Oh, no, so then I misunderstood you. I thought you were talking more about sort of time dependent.
Well, I mean, I'm just wondering, is there a way to parallelize the back solve so we can sort of be solving,
Right, so
get rid of the sequential solve, right? So we could start solving, more at once.
Right.
In some ways. I don't know if people have thought about that.
So then what you're saying is not just a multiple right-hand side.
No, it's one right-hand side, but I want to, say, solve it in parallel. So I want to say, do it twice. If you factor the matrix twice, right, then I can solve it twice as fast, right? Because the one factorization could start the solution for, say the entry number 1,000, right? Well, the other factorization could be starting to solve the solution at entry number 500, right? And so I could go twice as fast if I was willing to, if the factor is not really the important cost here, but it's the back solve. How do you?
But in most cases, it's going to be the actual reordering who's going to give you.
No, I'm talking about if you're solving the equation 1,000,000 times, right? The factor, back solve, all that is nothing, right? So I mean, the factorization is all nothing. Reordering, I'm thinking of a case where that's free, right? So you can do multiple factors, but I'm going to do 1,000,000 back solves.
Yes.
It's a time-dependent problem.
Right. Yes.
And so there I want to make my back solve. I mean, that's the whole cost.
Right, because then what we talked about here is that, say, each back solve is kind of 5% of the whole of the time, right? For LU, just one, but you are solving 1,000,000. Yes, I see that. Yeah. So that's, of course, is going to be more than 5%. And then you are wondering if it would be worth at some point to do another factorization. Is that?
Well, if you could, right? If you reordered the unknowns and had a separate factorization, right? Then the other factorization, the one factorization could initially be, solving for this entry in the matrix first.
Right.
Well, the other factorization could be first solving for another entry, right? So you could basically, with two factorizations, you go twice as fast.
I see. Yes. No, I have never thought about it. No.
And I haven't seen.
Yes, I have never seen it.
It's interesting to have this. Sort
But
of
maybe
Yes.
some,
No, I understand.
maybe you could use the same factorization, but sort of tweak it so you could sort of do that without having the full cost of two. Okay?
No, I understand the
Yeah,
question.
that's-
Oh, yes.
But it will have to be
Never thought.
I mean, the ones that, in this particular case, when you can factorize the LU without having to build any complex structure like the SuperLU, like the supernodal, or using the multifrontal kind of approach, but you will be doing something more simpler, yeah. Because these ones are very sensitive to the graph,
Yeah, so basically, basically the question was, here, what the slides had was basically the solution. Once you compute the LU factors, that takes very little time compared to the computation of the factors. But suppose you have to do millions of solves, right? So then perhaps you could do something else with the factorization. That was basically the... And I haven't seen anything like that. Thank you, Bill. That's a good point.
Another question? Okay, so anyway, we'll have a hands-on this afternoon on that. So thanks, Hosni again.